Welcome to this week's lesson on the normal distribution. What we hope to do here in about 10-15 minutes is overview the idea of the normal distribution, which many of you have seen before, I'm sure. Maybe not as formally as in a statistics course, but this is commonly referred to as the bell curve or a Gaussian distribution. And what we have here is a model, probability model, and I'm going to bring a picture over here to work with that we can this is right off of a TI-84 calculator, and I'll show you that in a little while. But the general idea is this graph of the normal distribution comes from a function, a mathematical function. And that mathematical function looks like this. So for those of you who are interested in the actual where and why, the mathematics of this would be coming from this function, 1 over, sorry about that, the square root of 2 pi e to the negative 1/2 x squared. When you do that on a calculator, you can get this graph, this model, and that would look like this in my calculator. I would have this function already typed in and then ready to graph. So that's where that model came from. Now, what we're hoping to do here is to actually be able to use this technology to evaluate probabilities on that curve. So what we're asking there is how rare is a value on this normal distribution. Before we do, some of the characteristics of this normal curve. As we can see here, it is symmetrical, so the left side and the right side are equal to each other. The area under the entire curve in any probability model is 1. So the entire area is 1. The largest part of this distribution has been between -2 and 2, what we call standard deviations. Okay, and you can see some of that over here to the left. And I'll be talking to you about that in a moment. But in general, it is a continuous curve, symmetrical, both sides, area, total area equal to 1. And that's what we want to now go ahead and work with as we move forward. So let me get you started here. Okay, there's the normal distribution, and I want to point out a few things to you here about this normal distribution. If we look at one deviation back, I remember what a standard deviation is from an earlier chapter in the course. Deviation is a measure of dispersion. So if we look from one deviation out to one deviation up, we are talking about 68.3% of the data falling in that area. 68.3% of the data falling in that area. If we go out another deviation forward and back, we will be talking about 2 deviations now, right? 2 deviations out and back. So that would be 2 deviations back, 2 deviations out. Out from what? Out from the mean. Out from the mean of the distribution. And again, that data, those statistical topics have been already covered in the course. But if we go from -2 to 2 deviations on this distribution, what we end up with here is a total of 95.4% of the data. So what that's telling you is in many applications we think about the middle 95% of this normal curve, and we'll see some of that later. That's where that's falling, between -2 and 2 deviations. And then the last thing that we talk about with this topic, which I haven't introduced yet, but I'm going to start calling the normal distribution, is if I'm between 3 deviations back and 3 deviations up, I'll have something called the entire empirical rule. And that empirical rule states that I would be from -3 all the way to 3 deviations at 99.7% of the data. So almost all the data in a theoretical normal distribution falls between 3 deviations back and 3 deviations up. So if we have applications where we're on on an integral standard deviation, it's pretty easy to compute. And that's from a thing called the empirical rule. So what I've just modeled here is the empirical rule on a normal distribution. So what can we do with that? Some really, really basic ideas. If I told you that male heights were normally distributed 69 inches tall with a standard deviation of 3 inches, what we'd be saying there is that the mean for an American adult male is about 69 inches tall, and that standard deviation is 3 inches. Okay, so just for the sake of an example, if I said what's the probability of finding a male randomly between 66 inches and 72 inches, that would be 5'6" and 6 foot. Well, the beauty of that is this falls exactly 1 deviation below the mean, right? 3. If I went back from 66, get ourselves a clean graph here. If I went from 66 to the if I went from 66 out to 72 on this distribution, here's what you would see. So here's our theoretical mean at 69. 1 deviation up gets me to 72. 1 deviation back gets me to 66. Okay? The area in between there, from my discussion earlier, is guaranteed by empirical data to be 68.3%. So that's how likely it is to find at random a male between 5'6" and 6 foot. Okay, so these types of applications, obviously this is kind of a benign application, but it's something that everybody can relate to, male heights. But this could be in manufacturing control, right, where you're talking about a desired part length or a time interval, those types of things. So this application can be better and better depending on how applicable it is to your individual major. Now, where the problem occurs is when you ask a question that doesn't fall right on one of these deviations, right? So if I said, what is the probability of finding a male less than, let's say, 62 inches, right? That is a situation where when I look at that on the curve, the next deviation back is 63. So 62 is somewhere here, and less than it is this area, right, that goes on theoretically forever. How am I going to find that? Well, what we have is this standard z-score, it's called, and that z-score, as you'll read in the text, allows you to standardize any score given the theoretical mean and standard deviation. So when you do this, you end up being negative 2.33 deviations below the mean, right? Because here would have been a negative 1. Here would have been a negative 2. And here's our score, and we're at negative 2.33 deviations. Now, what can we do with that? Well, in order to find area under a curve, we would need some geometric shape or calculus. And our course doesn't require either of those. So what we'd be looking for here is some form of technology to help us evaluate what is the probability of an x less than 62 inches, right? And we just did the work to standardize that to a z less than negative 2.33. And again, a quick sketch. Normal curve, 0 for the standardized mean, and if I'm back here at a z of negative 2.33, being less than that, it looks like this. How do I find that? We're going to use technology in our course, as we have to this point, called the Texas Instruments TI-84 calculator. And what I'll do for that is I'll have this type of look, and I can dial up the command distribution, right? And one of the first features of the distribution, we're looking for the normal distribution. So we're going to go to normal CDF, where the C stands for cumulative. And we are going to be able to, in a user-friendly dialog box, basically communicate to the calculator saying, hey, go do some calculus, and it'll do it for us. So we're going to start at the lower end of the curve, which this is a very small number, negative 1 E99. Right, so it's negative 1 times 10 to the 99th. That's a very large number in the negative direction, very far out in the curve. And we're going to run that up to our negative 2.33. And our theoretical mean is 0, and our theoretical standard deviation is 1. Why? Because we standardized. Okay, we changed it to a z curve. And when we paste that, we end up with the area that would be under the curve to the left of negative 2.33. This is a probability then. So finding a male less than 62 inches tall is about 1%. Right? If you rounded this would be 0.01. So about 1% of the time in the population that would occur. Now I want to show you a nice feature of the calculator where you can actually not be on the hook for all the arithmetic. You can actually say to the calculator, start at negative infinity. That's what our approximation is for negative infinity on a TI calculator. Come up to 62 inches tall for the male, given that most males in the theoretical model, the mean would be 69 inches tall, and the standard deviation is 3. It will do that standardization for you, the arithmetic for you, and then go ahead and find the area. So we'll get the same area. Now, when I say the same area, it's different at the 4th spot just because of rounding. I rounded back here, right? That was negative 2.33333. And here, the calculator didn't round. It did all the work for us. So that's the overview, and that's also a basic application using a TI-84 to find area. We will have more of this as we continue on. Your textbook will talk about it, and I will provide some other videos for this topic. If you have any questions on this, please come back and ask in the discussion boards, and I will gladly help. Again, that turned out to be roughly 1% of all American male adults being less than 62 inches tall randomly. Okay, so other applications more applicable to your field, examples coming, but that is the overview. Thank you very much.